Okay, Year 12s, welcome back to episode 9 of Math in the Bubble with your host, Mr. Daly. Today on the episode, we are going to basically just revise a few of the skills we've already learned over the past few weeks, but I'm just going to try and do some harder sort of examples. Alright, so parabolas. I wanted to revisit parabolas. Just because it's been some time since we've done a parabola problem. So this first one, I'm going to use the Vertex formula. So I might use it the way I showed you last lesson. So y minus y1 equals, well, y vertex equals a x minus x v squared. So this is slightly different to what I originally showed you because I had this y term on the other side of the bracket, but I've sort of just decided that it's better to have it like this because it's similar to the point gradient formula, which is essentially that, and then it's easy to remember because you can remember it comes from y equals a x squared. So this is a regular parabola that just fits through the origin, and the a is your shape factor, so that determines how wide or skinny it is, but it always will go through that origin. So when you've got your so the only thing that's changed is where there's a y, it's now a y minus how much you've moved it in the y direction, and then where there's an x, we've got it in brackets because it's x squared, but it's minus how much you've moved in the x direction. So to use this formula for a start, we have the vertex has been moved over there to 2, 3. So we can just plop those numbers in. Our y coordinate is 3, so y minus 3 equals a x minus 2 squared. Alright, now to find out the shape factor, we need a given point from the graph. So in this particular one, that's not going through a grid point exactly. So what we can actually use is one of the intercepts of the x-axis. So this point here will work. That's x is 6, y is 0. So we're going to put this coordinate into our equation. We'll call this equation 1. Star into 1. Ooh, I've got to move it up a bit. So star is going into 1. That star coordinate. So y minus 0 equals a 6 minus 2 squared. And this has worked out pretty good for us because that's just y. Hold up. What am I doing? That is completely wrong there. 0 is this y. And we've still got that minus 3 because that's part of the equation. So if I was to simplify that a little bit, negative 3 equals a times 4 squared. So our shape factor, 4 squared is 16. We'll bring that to the other side. We're going to get negative 3 over 16. So our final answer is y minus 3 equals negative 3 sixteenths x minus 2 squared. So you always have a y part and an x part in your graph. Alright, let's do one more. This time we'll start with the intercept formula. So that's where you have the opposite of these points in brackets. So y equals shape factor x plus 5, that corresponds to that coordinate where it crosses the x-axis, and x minus 1 over the other side. And we've got another given point, which is the vertex this time. So you can use your vertex point if it goes directly through a grid point as a known point to help find your shape factor. So that's y equals negative 2, x equals negative 2, which is nice because can't get them back to front. So negative 2 equals a x negative 2 minus 1. Hey, what usually happen? I'm pretty sure this happens every time, but when you put in the vertex coordinates, both your brackets and your tend to be direct opposites. So this is going to be negative 3, and then no, positive 3, and this is going to be negative 3. So you multiply those together, you get negative 9. So equals times negative 9. So our shape factor equals 2 ninths. So we put that back in our equation, back up here, and then we're going to get 2 ninths x plus 5 x minus 1. Whoops, there we are. Y equals 2 ninths x plus 5 x minus 1. Alright, moving on. So, I was going to do a circle intersecting with another circle, but I decided that might be a bit hard. So we'll actually start with a line intersecting a circle. So what this problem is going to be is trying to find these two intercept points for your line going through your circle. So first off, we need to write some equations. For a start, this line, it goes across 10, up 3. So it has a gradient of 3, rise over run, rise 3, run 10, x, and then our intercept is 2. Yeah. So whenever you're given a line and it's got the intercept, then you can just use your basic y equals mx plus c. Alright. Now our formula for our circle goes through 4 across, 2 up. So that is going to look like x minus 4 squared. So it's been shifted across 4 in the x direction. So that's where that minus 4 comes from. And then plus y minus 2 squared. So it's been shifted up 2 in the y direction. And that's going to equal 3 squared, because the radius is 3. Radius equals 3. So we have 3 squared. And then you can think of this as your a squared plus b squared equals c squared. Because you've essentially got a triangle going all the way around. Alright. Okay, so when we have an equation that's rearranged for y, what we can do is we can put it straight into where there's the y in the more complex equation, and do a bit of expand, because that would eliminate our y variable. I'll show you how that works. So what we're doing is we're going 1 into 2, so that looks like x minus 4 squared, so nothing happens to that because it doesn't have a y in it, plus 3 over 10 x plus 2 minus 2 squared, and that equals 9. We're going to do a lot of expanding, so I'll just evaluate that 9. Alright, this is handy, those cancel out, so we're not going to get any extra terms going on there. When we expand out this set of brackets, we're going to get x squared, and then our middle term is twice that, minus 8x, and then our final term is this squared, so that'll be plus 16. And then we're going to, well, everything is apart from this has been cancelled out, so we just want to square this term. So that would, when you square something where all the things are multiplied together, you're just squaring each element. So 3 squared over 10 squared x squared equals 9. So the only like terms in this situation are x squared terms, and also our numbers. This is going to stay the same, so we end up with x squared what I'm going to do is I'm going to change that to 100 over 100, because this is going to be 9 hundredths x squared, and nothing happens to the minus 8x, and the 16 will get 9 subtracted from it, so we got 7 equals 0. So to do this really quickly, we could just cancel that out and make that 109 x squared over 100. Alright, so our term, what we actually have here is a quadratic. It's kind of complicated for a, but everything else is pretty easy. A is 109 over 100. It might be actually better to make that decimal. That's going to be 1.09. That'll save us some time. equals that, B equals -8, and C equals 7. Are we still on? Oh, alright, just scooch up a bit, Mr. Daly. Okay, right, quadratic formula. So, quadratic formula, you're going to be using this a lot this year. Minus b plus or minus the square root of b squared minus 4ac all over 2a. So we've got a negative b, so this is going to cancel out this negative, so you get 8 plus or minus square root of 64, that's -8 squared, minus 4 times 7 times 1.09. And then that's multiplied by 2 times 1.09, which is going to be 2.18. Alright, and I'm going to put this whole thing into the brackets, even though I advise you guys not to do that. But if you ever do that, just make sure you put a bracket around all of that so that it forces it to make that calculation before it takes a square root. 8. Oh, and actually, we want a bracket here as well, because we're going to be dividing the whole thing by 2.18. So actually we want to do bracket 8 plus square root of 64 minus 4 times 7 times 1.09 bracket, and then we want to get outside our square root, so that can be a little bit, because we want this bracket to be outside the square root so that it includes the 8. Divide that by 2.18. First answer is 6.32. 324. So remember, this is our x1. Our graph actually goes through both. So our x2, what we want to do is just change the plus to a minus. So you can just skip back through in your calculator. .016 for significant figures. Alright, so that will correspond to that one, and that will correspond to that one. And that looks about right. Now, the last thing you always do when you've calculated x coordinates, you need to find the corresponding y coordinates. Now, you can actually put these back into here and solve for y that way. But why do that when you have a line equation, which is much simpler? You're just going to, and it'll spit out the answer immediately. So y1 is going to be 3 over 10, 6.324, and then we're adding 2. And then, so that'll give us an answer. And for y2, it'll be 3 over 10 times 1.016 plus 2. So this this is just equation 1 into here and here. That gives us 3, 10, 6 times 6.324 plus 2, 3.897. And then we just want to go back and delete that number and change it for 1.016. Sorry, I haven't been very good at getting everything on the screen. 2.305. So your x1 goes with your y1, and your x2 goes with your y2. Yeah. So this is 0.1. Ah, never mind. Okay. So I'm gonna just, where's OBS? Turn the drawer cam off. I just want to show you something on Desmos quickly. So if we have an equation y equals 3, well, let's go 1.5 to the power of x, it looks like that. Now, what a powerful thing that you can do is, say you want this to go through 4, and so you want your exponential to be multiplied by 4. But so if you go 4, shift 8, which is the multiply asterisk, now your graph, your exponential goes through 4. Okay. Now, what I wanted to do was to see if I could match an exponential on top of that. What would that look like? Because obviously our location point is going to be somewhere around here now. So this multiplying by 4 in front of an exponential has the effect of shifting where it crosses the x-axis up. So sometimes you want to do this because you're doing an exponential decay. So you might have, which is topical right now because we're in coronavirus is in decay. So we might have 200, and then we might have instead of a number higher than 1, we have a number less than 1. So I'm just going to zoom. So what we got here is something that you might want to your graph to represent is the decay from maybe 200 cases down to maybe, well, it's at the moment it's going to asymptote at 0, so you might want to know when the last case is going to be with this sort of decay. It gets very close to that. Maybe not 1. When's the last 10? Okay, just for argument's sake. So that's going to intersect our graph down here at 13.42510. But say you wanted to, you knew one point of data was that the last 10 people to have coronavirus happened on day 10. So you wanted it to go 10, so it would go through 10, 10. How do you change your exponential graph? So, well, that is this number. So what we want to think of is this is A. We'll just put a slider on there. So we used to have it at 0.8, but it's got to be a bit lower than that to get to go through 10. So let's try and calculate what it would need to be. Okay, I'm just going to turn that Droid cam back on. So I'll just do a rough drawing of what's going on. So we've got some exponential decay. It's going through 200 at day 0, and at day 10 there's 10. So this is your cases, and this is your days. And we want to know the shape factor of our decay curve. So we have this coordinate to work with. So this is 200 times this exponential decay graph. So normally it would look like that, but it would go through 1. So it's just been, what's happened is it's been multiplied by 200 so that it goes through 200. Alright, so what do we know about this point? This is when y equals 10, x equals 10. So 10, if we substitute that in, equals 200 times a to the power of 10. Okay, this 200 we can divide by 200 both sides, and that'll get rid of that. So what we have is 1/20th, 0.05 equals a to the power of 10. And believe it or not, you can do the 10th root. It seems like a ridiculous thing to do. If you do the 10th root on both sides, so 10th root of a to the power of 10 is going to just be a, and the 10th root of 0.05, well, we've got to use our calculator to do that. Okay. remember that little symbol x square root? Well, you just put that after you do shift 0.05. Is it going to equal? So it's saying that our shape factor needs to be 0.7411. So let's go back to Desmos and put that in and see how it turns out. Going to just change A to be 7411. There we go, and now you can see that it's gone directly through that point, well, almost directly, but remember, you know, that was a 10-digit never-ending sequence, but it got pretty close. Alright, I might end that there. So, new learning for today is that you can, another way to tweak your exponential graph is that you can multiply a regular one and it will scale it up so that this intersection point with the y-axis is that number. So this is your new y-intercept. Yeah. Of course, you can still bump it around by doing things like that. That will bump it one to the left. So then you would get a point -1 200. And you could also bump it up by going y -4 would move this up 204, but it also move it up the asymptote. So you might want to do that sort of thing to move where the asymptote is. So if you had your equation y -4 equals 200, let's go 40 actually, so it's a bit clear. What would happen to this graph? We'll use this 0.7411 x. Well, this is what would happen. You would get, now it wouldn't go through 200, it'd actually go through 240, and then your asymptote down here would be, oops, sorry. So the new graph would look like this. There's 10, so it's still going to go through the equivalent of 10, 10, so it would go there like that, but your asymptote has been bumped up by 40. So everything's been shifted up by 40. The intersection at 200 has been shifted up by 40. The intersection at 10, 10 has been shifted up by 40. So now it's at 50, 10. So there's a couple of ways to manipulate an exponential graph. Yeah, similar to, you know, there's multiple ways to do parabolas. Yeah, okay. Seems like you guys don't seem to have any more questions, so I mean, I'll wait a minute, but I think that's all that we'll do. Thank you for tuning in, though, even though it's just two of you. And William. I hope that made sense to you, William. Did you stay for the whole thing? how do we know which equation to use for the parabolas? Well, a lot of the situations, the only one that will trip you up is, um, so you could have used either for both of these, but the one that would trip you up, Jack, would be if you didn't have any intercepts. So there's situations where you get a floating parabola. It doesn't cross, if it doesn't ever cross the x-axis, then you can't use the intercept method, which is, I kind of I favor the vertex method for that reason. But sometimes you're not given the vertex. Like, for example, you could be given this sort of thing where you've got your vertex. Who knows where the vertex is there, but you know where this point is and you know where this point is, and then you could also know maybe this point down there. So either will work